right, so this session now is a little bit different. It's meant to be a bit more interactive, and it's about programming a quantum thought experiment. So it has two parts of this. One is why and how one goes about this, and the other one is like, oh, what do we actually use to program a quantum thought experiment, right? So Nuria, which you know because she's been she's been doing as much work as me, just a bit less shouting at you. So she'll talk about the how and the kind of the framework we have for modeling quantum thought experiments, and then we have Damian from Huawei, which is one of our sponsors, supporters. We're very grateful. They're very peculiar about and precise about what words we can use.
No, here you can say whatever you want.
I can?
Yeah.
Okay. Good. And so first Nuria will motivate this, then Damian will talk about Project Q, which is this quantum programming language, and we'll help you install. Also, the links are on Discord if you want, and then if you want, you can try to customize the software we have, which would be very cool.
Yeah.
So I'll leave you with that.
Okay, thanks a lot for the introduction, Lydia. So for first, I'll give you a shortish motivation on why quantum programming might be useful for foundational questions. And then Damian will tell you how to use this quantum programming tool. And so then you'll be able to model your own thought experiment. Okay, so let me first motivate why we're looking at the thought experiments in the first place. So in science, we often use these thought experiments to analyze the theory and explore the theory and its limitations. So for example, twin paradox in special relativity or Maxwell's demon in quantum thermodynamics. And all these thought experiments, they're meant to tell us more about how we should understand the theory and what exactly theory permits and what it doesn't. And in quantum mechanics, such thought experiments are usually used in formulating no-go theorems, which would then, for example, help to rule out some interpretations of quantum theory. Of course, this is all very nice and very conceptual, and this is simply fun from the conceptual point of view to look at these questions. However, there is also a non-conceptual motivation to it, which is, so assume first just a simple classical setting where we have a network of classical computers, and they would like to reason about each other. Or they would like to reason about some event which happened somewhere else in the framework. And then we would like these computers or agents who have certain knowledge and manipulate with that knowledge to reason consistently about it and give us conclusions and results that we can trust, that are consistent with what is happening in other parts of the framework. So to explain what I mean by consistency, let me start with a very simple classical puzzle, which is that there are three physicists, maybe attending the summer school, Alice, Bob, and Charlie. And after a long day of lectures, they come to a bar, and then they want to order, and the bartender asks them, does everybody want wine? And then the following scenario ensues. So first Alice says, I don't know. Then Bob also says, I don't know. And then Charlie happily proclaims yes. So how did Charlie come to this conclusion that indeed everybody wants wine? So what they did is they imagined themselves on Alice's place, and they thought, okay, if Alice wouldn't have wanted wine, then she would have said no, because Alice is a logical person, and if she doesn't want wine, then not everyone in the group wants wine. But she answered, I don't know, which means that she does in fact or would like a cup of wine. The same goes for Bob, so Charlie just assumes Bob's reasoning position, and similarly comes to a conclusion that Bob would also like a glass of wine. And finally, Charlie themselves would like a glass of wine, and so they answer yes for the whole group, and this is consistent with everybody's desires. So we would like the same consistency to hold for any network of agents in whichever theory we model them with, and for whichever theory they model themselves in, including quantum theory. However, for the particular case of quantum theory, this proves to be hard. For example, in a quantum thought experiment devised by Frauchiger and Renner around 4 years ago, we have agents who are using quantum theory and modeled within this theory who reason about each other's outcomes, and they come to a contradiction. We will cover this example in a bit more detail in a few minutes. And this contradiction result, is derived upon a number of assumptions. So the assumptions concern how the agents are modeled, how they reason about each other, and how their reasoning about each other is combined, essentially. Okay, so you've just seen an example of a reasoning agent in a classical setting, and now I will give you an example of a reasoning agent in a more quantum scenario. Then we'll see an example of how can one model measurements and model reasoning when we model agents within quantum theory, and in particular model agents as a set of qubits on a quantum computer. Then I'll briefly talk about the structure of the software package that we have, which would allow you to model any setting where agents are reasoning about each other, where quantum agents are reasoning about each other. And then we'll go through the Frauchiger-Renner example, which is also implemented in the software. So you can find the link to the software and the GitHub repository in the Discord chat. And there are several Jupyter notebooks which explain step by step how to build your thought experiment. Okay, so let me give a quantum example. So suppose that we have an Alice in her lab, and she has a spin system, R, a qubit, say. And initially, this qubit is in the state that you see here. So 1 over square root of 3, 0 plus square root of 2/3, 1. And what she does, she measures that state, and in the computational basis, which is a 0-1 basis. And if she gets 0, then she prepares another system, another qubit S in a state 0. And if she measures the system R in a state 1, then she prepares a system S in a plus state. And then she sends the system S to Bob. Then Alice finishes her job, very quickly walks out of the lab and goes to the bar to have a wine. However, now Bob arrives to the lab, and he's very curious about which result did Alice get in her measurement. But everything Bob has access to is the system S. So Bob measures system S, gets outcome 1, and now he wonders, oh, what did Alice get? I cannot ask her directly, she's already gone, but maybe I can reason about it. And indeed, so he can reason with certainty that Alice got outcome 1, because he starts thinking, okay, if she would have measured 0, then I would have measured 0 with certainty, because if Alice would have measured 0, she would have prepared the system S in state 0. However, he measures the state. He measures B equals 1, which means that the only possible option for the A's measurement is A equal 1. So this is an example of how a quantum, say an agent, not yet quantum, just an agent can reason about other agents' outcome depending on their own. Okay, but now what we want to do, we want to model the agents themselves as well as quantum systems. And for that, we need to be able to model the measurement of an agent. So what happens when an agent measures a system? So first, let us consider just the usual physics course example of what measurement is. So for example, let us look at the Stern-Gerlach experiment, which allows to measure a spin of a particle. So we have a particle which undergoes interaction with the magnetic field of this magnet. And after this interaction, we can see on the screen different locations depending on whether the spin was +1/2 or -1/2. And this interaction is carried out via turning on the interaction Hamiltonian, which effectively couples the spin of the particle z to its degree of freedom of moving in y direction. And this can be seen as just implementing this unitary for the time t. So basically, in this context, it's just the turning on the coupling Hamiltonian. If we look at now, let's say a more quantum computing example, so we can model Alice as a qubit who is measuring in its own turn a qubit R. And here we also perform the measurement as a coupling, namely a unitary C0 gate. And in this context, it's good to look at the first thought experiment in quantum mechanics, which is called Wigner's friend. So we have Alice in her lab, who has a qubit R. And outside the lab, we have another agent, Wigner. And they're both trying to understand what the state of the lab is. And here we can have two different views on this situation. So first we have a view of Alice, who measures the system R. And for Alice, the system R collapses in either 0 or 1 state. And then we have the point of view of Wigner, who is outside the lab, and hence models the evolution of the lab and the interaction between Alice and system R as a unitary, in this case a C0 gate. So for example, if Alice's initial state of the memory is 0, and she is measuring the system R, which is in a state alpha 0 plus beta 1, after applying the C0, the joint state of R and A becomes alpha 0, 0 plus beta 1, 1. So if Alice measures system R in state 0, she writes down the 0. If she measures the system R in 1, she flips the state of her memory. And from this example, you can already see that somehow applying the rules of classical reasoning and classical intuition is not so straightforward in quantum theory, because this simple thought experiment shows that there is a certain dichotomy of views on the same physical setting that here Alice and Wigner have. Okay, so this is one of the examples how one can model the measurement process of Alice measuring the qubit R. Okay, so now what we want to also incorporate in our model is this process. So how do we represent operationally the reasoning process of Bob when he tries to reason about Alice's outcome? So not only measurement, but also reasoning about others' agent outcome. And we come back to this example that we had before. So one example, one way to do so is the following. So I represent here everything in terms of the quantum circuits. I hope you're familiar with this picture. Is everyone familiar with quantum circuits, more or less. So you read them from left to right, and this is the sequence of operations in time. And from top to bottom are the systems on which the operations are performed. So what does Bob do when he comes to the lab? He has access to the system S, which is in some state psi. So first he measures the system and writes down the result to his memory qubit, to his first memory qubit. Then he does the same reasoning process as we just did with you a few minutes ago. And based on that reasoning process, he can initialize 2 reasoning qubits, or inference qubits, so to say. So the first inference qubit corresponds to the statement of, can I say anything about anything deterministically with probability 1 about Alice's outcome if I get outcome 0? And the second corresponds to, can I say something with certainty about Alice's outcome if I get outcome 1? So if I can say nothing certain about Alice's outcome, if I get outcome 0, and this is true, then the state of the qubit, of the inference qubit, is 0. So I don't do anything with the state. And if I can say something certain about Alice's outcome, so if I get outcome 1, then it follows that Alice gets outcome 1 as well. Then I initialize that inference qubit in a state 1. And finally, the last element is a prediction qubit of Bob, which stores his prediction about Alice's outcome. And to write that prediction down, we need to perform 2 operations. So first we check for the case when he gets outcome 0. So here I have the Toffoli gate, so-called, which has 2 controls. So if the state of his memory is 0, so if he measured 0, and if the corresponding inference qubit has some certain prediction, so if it's in a state 1, here that's why the dot is black, then I update my prediction state. And the second update corresponds to the case of Bob getting outcome 1. So if he gets outcome 1, and if I can say something certain in that case about Alice's prediction, then I update my prediction qubit. Is it more or less clear how this process works? Please ask any questions if this is not entirely understandable. Okay, no questions. So this is just an example of how one can do it. We don't claim that this is the most efficient example. Probably you can try to use a bit less qubits for each agent. Maybe you can use the same qubits for several agents. But this is also up to you to optimize if you want. Okay, so having these 2 important bricks of how we model measurement for the agents and how we model reasoning for the agents, I can now talk a bit about the structure of the software and what you can vary in the software. So basically, the idea is that you can have any protocol between any number of agents where you can specify things that, oh, Alice measures system R, Bob measures system S, Bob tries to infer Alice's result, some Wigner comes and measures Alice and R together, and Wigner then tries to say something about Bob's result, and so on. So this is very arbitrary. It can be arbitrarily long. And it will take care automatically about how many qubits it needs to allocate for memories and so on. Then there are modules, which are the following. So it's the agent, which concerns how the agent is modeled, and how the reasoning is modeled, and how the measurements are modeled. So as of now, it is implemented in a way I just described. But of course, this is maybe you don't like this, or maybe you have some objections, or maybe you can optimize it. So this is up for a change. Then there is a logic module, which concerns the logic of the agents and how, for example, their inferences are combined, what we count as paradox and what we don't. And as of now, every agent can combine inference with everyone, and paradox is the usual sense of getting a statement and the negation of that statement. But this can also be changed. And finally, the interpretation. Here you can introduce different. You can try to formalize different interpretations of quantum theory, and also, in particular, how the predictions of the agents are made. So if you remember the reasoning circuit that we had before, the things that came from outside the circuit were the initialization of the inference qubits. So the way we decide how to initialize inference qubits comes from what theory we're using, in particular, for example, which interpretation of quantum theory we're using. So for example, you can have a module where you say, oh, I'm modeling agents in a Neo-Copenhagen approach, which means that the cut is subjective, so the separation between quantum and classical is different for different agents and different points of view. And then you can say, oh, each agent models the evolution in other agents' lab as unitary. Or on the contrary, you can say, no, every time an agent makes a measurement, it results in a collapse. And that would be more towards the collapse interpretation. But you can test different approaches and different ways of how agents model each other. And then, having specified all these things, the program will run your protocol, and it will tell you whether the agents come to a contradiction or not. Okay, so why am I talking about contradictions? So now it's the time to explain why the contradiction can arise when we use quantum theory. And for this, I will return to the famous example of Fraufinger and Renner I mentioned a bit in the beginning, and go step by step. So luckily, we already discussed half of this setting in the beginning when I was talking about Alice and Bob and their different times of coming to the lab. So let me recap. We have an agent Alice, which we model as memory qubit, initially in the state 0, which has a system R, which has a qubit initially in this state. Then what happens, Alice measures the system R in the computational basis 0, 1, and writes down the result to her memory. And she has a system S, which she initializes depending on her result, the same way as before. So this is the intermediate state of systems R, A, and S. Then she sends the system S to Bob, and Bob measures it in computational basis and also writes down the result to his memory. And after this is the state of Alice's lab and Bob's lab combined. Then we introduce two more agents, Ursula and Wigner, who are outside Alice and Bob's labs. And they measure Alice's and Bob's labs respectively in so-called OK fail bases. So they're written here, they basically are Bell bases. Then given this setting and given these measurements, different agents can reason about each other's outcomes. And this is the summary of their conclusions. So one of these conclusions, namely that if B measures 1, then A measured 1 with certainty. You've already seen how this arises. And all the others can be seen arising in the same manner. So for Alice, if Alice measures 1, then Wigner measures fail. If Ursula measures OK, then Bob measures 1. And finally, the Wigner says a slightly different statement. He says that, oh, there is a probability that in some round of the experiment, both myself and Ursula will measure OK. So this is let's say, a post-selection part of the experiment. And combining all these statements and post-selecting on the round where Ursula and Wigner both get outcomes OK, we can combine the statements. So we combine from U equals OK follows B equal 1, from B equal 1 follows A equal 1, from A equal 1 follows B equal fail. We will get that in the same round Wigner gets OK, but agents can reason that he gets a fail. So hereby we arrive to a contradiction. Okay, and as I said, this contradiction is derived based on various assumptions which concern exactly how the agents are modeled, which logic they use, how they model each other, and so on. And these are all the things that you can vary in our framework. And so, for example, as logic, you can choose your favorite axiom system. You can, for your favorite reason, restrict which inferences can be combined or not. For example, if agents are not allowed to have different Heisenberg cuts and so on. You can modify the model of the agent. You can formalize your favorite interpretation of quantum theory. In fact, this tool, I think, is specifically a great motivation for people to formalize what they mean in different interpretations of quantum theory. Currently, we have 2 implemented, which are Neo-Copenhagen and collapse theories. I briefly talked about them before. Yes, and you can input desired communication protocol between your quantum computers, quantum agents, and it will give you the conclusion whether your chosen set of axioms that you input is consistent or inconsistent. So do agents in this particular protocol that you want to test come to consistent or inconsistent conclusions? Okay, all this software was developed on the basis of Project Q, which is one of the quantum programming languages developed at ETH, in fact. And now I thank you for your attention. Please check out the GitHub repo. And now Damian will give you a crash course on how to use Project Q and its machinery. And after that, when you get acquainted with Project Q, we can try to model some thought experiments on a quantum computer. Yeah, and if you have any questions, please come up to me at any time. Do you want the charger?
Yes, I might need to.
Okay.
I don't know what to put that. Okay. That's the wrong one. Very good. Where am I? Oops. Okay. Hopefully it's good. Good afternoon, everybody. So I'll be talking, hope you can hear me well. I'll be talking a bit about Project Q. I'm one of the maintainers. Project Q, and it's, as Nuria said, it was initially developed at ETH. Huawei has been contributing to it a little bit. Sorry?
Your second microphone on?
The other one, yes.
Yeah, it's on.
Maybe I need to tweak this a little bit.
No, I can hear that it's coming from the speakers.
Oh, yeah, I can hear myself too. So, anyway, so Huawei contributed a little bit to Project Q. We're still in the process of merging a few features, although in the future we might be also doing our own stuff. But that's not the story for today. So the idea is just to shortly show you how to use Project Q, how to allocate qubits, perform gate operations, so that you can do your own examples afterwards. I also have an installation section. I had a quick look over it today. It should be up to date, but if you have any troubles afterwards, just let me know. And for sure, we can manage to install it on all of your systems. So the Project Q framework was initially developed at ETH. And this is a bit of marketing words just saying that, well, it can do most of the things that you need to do for quantum computing. It's not as active as some of the others, like Qiskit, but for most of the things you want to do, so manipulating qubits, applying gates, doing measurements, implementing algorithm, you can also do it with Project Q. And the syntax, I think, is fairly simple and easy to understand. It's open source and free. Hopefully, it's just okay. It's extensible and it's been thoroughly tested anyway. So these are some of the 2 papers that, if you want to cite Project Q, you can use them. But if we go directly into the more details on how to use Project Q itself, so the syntax comes from the physics initially as the inspiration. So typically what you have in physics is you have an operator that's applied on a set of qubits, or a set of quantum states, sorry. And so the syntax in Project Q just mirrors this. Imagine that you have this here, but this is not valid Python syntax, so we have to drop it. But that's essentially the core of the syntax itself. So you always have the operators on one side, and you have the qubits on the other. So this is, as an example, a short, simple random number generator in Project Q. I will go through this example line by line. I will also put the slides on the website afterwards. So the main, so Project Q is a Python package. The main packages you might be interested in, at least for today, are the top 4. And I will cover mostly those. The other ones are if you want to do more, I mean, this is mostly for internal purposes, but the other ones are more if you want to do, if you want to run it on an actual hardware, for example. In setups, you have ways of mapping your quantum circuit to the IBM quantum computing computers. Also, INQ is supported. Microsoft Azure is also coming at some point. So these are for more advanced uses, so to speak. Allocating a qubit is easy. You basically call the allocate qubit method. If you want to allocate more than 1 qubit, then either you call allocate qubit more than once, or you can just call allocate qreg, which essentially does this for you. For as far as Project Q is concerned, quantum registry is just a list of qubits. So nothing more, nothing less. So if you know how to use a Python list, you know how to use quantum registry in Project Q. I should also mention, if at any point in time you have questions or something that's not clear, just let me know. Then if you have measured a qubit, you can access the result of the measurement by simply casting the qubit object itself to an integer. And one of the safety features, so to speak, of Project Q is once at the end of your program, if the simulator detects that one of the qubit is not in a classical state, meaning that you most likely have forgotten to measure it, you will get an error, basically saying that this qubit has not been measured or uncomputed. This is most likely a bug in your code. It might be a bit annoying sometimes because you, even if you're not doing anything with the qubit, or you know something, you know it's a qubit you're not using anymore, Project Q kind of, at least the simulator, kind of forces you to measure it. But this is also a good way of catching some bugs. For example, if you have an algorithm where you compute something and then you want to uncompute it, if you make a mistake, then when uncomputing, then this would catch those kinds of mistakes. The allocating qubit is as simple as deleting the qubit object or calling the destructor. If you have a quantum register, you can delete the whole quantum register at once. And as I mentioned just on the previous slide, you should only deallocate qubits if they are in the classical state. So if you have a qubit that is not in a classical state, just measure it before deleting it. I should mention also at this point, in Project Q, there's no real concept of quantum circuits per se, because this is more of a view of if you want to apply the quantum circuit on an actual hardware, at least on the hardware we have today. So Project Q doesn't limit you to that. You can allocate qubit at any point in time. Since you're mostly going to run these quantum circuits on your own machines and not on actual hardware, most likely, you won't run into issues. But there's no constraint on saying you need to allocate all the qubits at the beginning of the program and delete them at the end. You can allocate them and delete them whenever you want. The simple gates, I've put the definitions up here on this slide for reference. But these are all the usual suspects. So the Pauli gate, X, which is also called NOT if you want, YZ, all the rotations. So maybe it's important to remember if you're at some point implement something in Project Q, you want to port it to some other languages, such as Qiskit, for example. Pay attention to the definition. For example, RZ is often not defined exactly in this way, or R and PH sometimes are defined, or sometimes they have different names, but sometimes they have also different definitions. For example, in Qiskit, RZ is actually R in Project Q, because we have different definitions. So if you are juggling between different quantum software packages, just be aware that sometimes the definition of the actual gates might be different. That's mostly true for the rotation gates, like X, Y, and Z, and S and T are usually well defined, but you have some play around that you can have with the other gates. And to use them, these gates are all in the ops submodule. So just import them from there, and then to apply them, simply it's the gate itself with the pipe symbol, and then the qubits you want to apply them on. Exactly. So then there's also some other gates. So C0, control Z, TOEFL, swap, and all that kind of stuff. If you have more than one qubit, typically what you do is you have the control qubit first, and then you have the target qubit. So in the case of the TOEFL gate, which is just double C0 if you wish, you have the two control qubits first, and then you have the target. So that the order is important. Yeah. So this, to come back to that, we have covered almost everything on this slide already, except maybe for this. Line number 10, which is important because of the way Project Q is actually processing your quantum circuit in the background once you want to actually execute it. So the instructions are not executed necessarily immediately. So Project Q gives you no guarantee as to when actually the quantum instructions are going to be actually sent to the simulator or to the backend that you have. So if that's a quantum hardware machine, then that's also possible. But Project Q doesn't let you know when, because it might do some optimization in the background. So if you want to be absolutely sure that all the gates that you have sent up to this point of your quantum algorithm to the simulator or to your quantum hardware, you should call the flush operation. And this will make sure that all the gates up to this point have been passed on to all the compiler engines and that everything has been synchronized with your backend. So if we go a little bit beyond simple gates, so we support what we called meta operations, so tensor gates, essentially applying a single qubit gate onto multiple qubits. And I will spend also some time talking about control and dagger operations, and maybe also a little bit about compute and compute. Loop is not so interesting. So if you have some control gates, yeah, so first of all, if you want to measure more than one qubit, measurement is a single qubit gate. So if you want to apply it to multiple gates, multiple qubits, sorry, what you essentially do is just call all, and in parentheses, the name of the gate you want to apply on all the qubits. And this works for any kind of gate in principle. And if you want to do something else than C0, you can use the shorthand C with, in parentheses, the name of the gate. If you don't specify anything, it's a single control with the gate. And otherwise, you can specify the number of control qubits that you might want to have. Although I wouldn't recommend using these two bottom syntax as much, and I will come to that later as to why. So here's a small toy example. I'm implementing maximally entangled state, or also called Bell state. One way of doing it is the standard way, so to speak. So you apply, so you allocate your qubits. You apply H, so a Hadamard gate on the first qubit, and then you basically do C0s on all the other qubits, with the control being on the first one, which essentially guarantees you then, if you work it out, that at the end of the day, you will get either full 0 state or you will have full 1 state with exactly 0.5 probabilities, or 50% chance of one or the other. Essentially because this qubit now, because of the Hadamard gate, is like 50-50 between 0 and 1, and then you constrain it with the C0 operation. So then all of the qubits are either 0s or 1s. Now, if you have, now that was the example with 2 qubits, you have more than 1, more than 2, sorry. The question becomes what to do here. One way is to do this. So you basically do Hadamard gate as a before, and then you just basically just C0s everything else based on it. So if you take this one step further, if you have, let's say, 5 control qubits and another gate that depends on 4 or something, this slowly becomes quite ugly. So one way of doing it is like this. I mean, you can shorthand it like this, obviously. But this becomes is not really maintainable because first of all, you have to make sure that this length here matches this one here, and so this becomes ugly very fast. So this is highly not recommended. Now, the way you typically do it with Project Q is you use the control operation. And what this does here, if you are familiar with Python, you might know that if you want to open a file, you typically should use with open as fd or whatever name, because this construct guarantees you some exception safeties and stuff. And here we are actually using it in order to simplify a little bit the syntax with control qubits. So essentially what this does is anything that is in this block here is going to be controlled on the qubits that you pass on here. And that's it. So if we go back to an example from previously, essentially what you would do is do something like this. This also is much nicer to read in a way because it's exactly clear what you are currently doing. So you know exactly where the control qubits are, and then you also have you can also have more than one operations. So if you have, let's say, 10 operations you need to control on the same qubit, here this appears only one, and you can easily find them again. The other advantage of this is you might be able to give some opportunities to the compiler to do some more operations, some more optimizations. Same thing with getting the inverse of a gate. You can obviously call get inverse, but again, that's not usually recommended. What you would do is do simply with dagger. And this would essentially take the list of all these operations, invert all of the gates individually, one by one, and play them in reverse order, because that's the way you get the inverse of the quantum circuit. There's the same thing with loop, although there it's less obvious because essentially it's doing exactly the same thing. If you look at the code, that's exactly what it's doing. So for loops, it's not as interesting. Maybe one last one is in lots of algorithms, for example, maybe Grover you've heard of, there's a lot of things where you have to compute something, do something else, and then uncompute the first thing you did. And there's a construct for that in Project Q. So you just say with compute, you put whatever operations you need to do the computation. Then once you exit the block, you can do whatever else you want, and then just say uncompute. And the compiler is smart enough to know that you need to play the operations in reverse order and invert all of the gates. And then in some cases, you might want to do better compute. There's a few examples, even within the Project Q code, where there's custom in compute. You might say that this is a bit dumb to do this, because now if I'm explicitly writing how to invert the thing, then why am I using this construct? The main reason is you give the compiler more options when it comes to optimizing your code. So for example, if you would do something like this, where you do control A on something, do a control U afterwards on the same qubit, and then do the inverse, so typically do something, uncompute the first thing, you get something like this. So you can see here that all the code is controlled on all the qubits, as you ask the compiler to do. But if you use these constructs, you allow the compiler to actually optimize your code and make sure that, for example, A and A dagger are not controlled on the qubits, because it's not actually needed. Quick words about backend. So the default backend is a simulator. This is the default, so it just creates a normal simulator. There's some other backends to print out the commands, draw a circuit. There's actually a support for matplotlib if you're using Jupyter notebooks. Yeah, this is just a few slides showing examples how they work. So basically, the resource counter just prints out whatever you gave him as an input and just show you statistics about your quantum circuit. Command printer just prints out the actual commands. Circuit drawer draws. Circuit drawer draws in LaTeX. The matplotlib obviously uses matplotlib. And IBM allows you to run your code on the IBM Quantum Experience. Yes?
When is a good time to make a break?
Right about now. Because I'm just getting to the end of this, and then it's installation time. So just a recap of what we've seen. So allocating qubits using gates, measurements, doing tensor operations. In this sense, that means just performing the same operation on multiple qubits. Meta operations with control, inverting operations with dagger, and compute and all the rest. And with that being said, I've been bombarding you with information for God knows how long. Now we can make a break, and then when we come back, I can show you a few more slides on how to actually install this on your machines. Any questions? Was I super fast and you all? Yes?
Just conceptually, what exactly is the main engine doing and why is it there?
So you need, as in any language, you need a convention on where to start, right? So if you have C or C++, it's the main function. Why is it called main? We just need to make some decision as to what's your main point of contact with the language. So the main engine is essentially responsible of tracking all the qubit allocations and everything that is related to them. Meaning you can have two different, so a main engine is responsible for allocating qubits and performing operation on those qubits. And you can conceive a way of having multiple main engines that have all of them have their own sets of independent qubits. So it's just a design decision in Project Q where everything starts and ends with the main engine. It's similar in approach, if you would say, like what Qiskit has with the circuit objects, where you perform operations on the circuit objects. In the case of Project Q, it's called the main engine. Does that answer your questions?
Yeah, I guess.
Not quite.
Yeah, I'm not 100% sure. I mean, what exactly does it do? I mean, you already have Python, right? You could use Python to have all this backlog and all that stuff. So
Yes.
what exactly is the need for this interface that the engine is?
So you need to be able to, so for example, for the qubits themselves, at some point you might want to perform some measurements on them. So something somewhere needs to keep track of whether a qubit was measured or not. So you could encapsulate all of this into the qubit object itself. But in this case, it's the main engine that's responsible. The other thing I haven't talked much about that I can probably show is actually what Project Q does is it takes the commands that you're sending and then it's passing them through a list of compiler engines that are doing various operations on those instructions. So you might say, I want to perform a CNOT operation or TOEFL operation on some qubits. But let's say the hardware that you have does not support them. So essentially, if you use, I mean, you can configure all of this, obviously. But the default thing would be, for example, saying, OK, I'm not actually allowed. You're actually asking me to perform an operation that is not allowed on the actual backend. So I need to do something with this operation in order to make that happen. So either I can make that happen, meaning I can decompose it in a set of gate that is possible to run on the actual hardware. And so the main engine is the one that is the head of the linked list of compiler engines that are passing the operations between one another. So in that sense, the main engine is also the one that keeps tracks of that. So that's what is your main point of entry. But yeah, that's one way of designing it. Obviously, it's not the only one. Any other question? Break? No break?
Okay, let's take a 5-minute break.